Okay, so actually the total strength should be 100 because said one batch has joined and 72 of the X1, X2 and X3 should be there. X4 only should move out. The rest of the students should remain in the class. Okay, because today, although it's the theory time, but we are discussing the practical work. Are you getting what I am saying?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So the next experiment is determination of ion exchange capacity of an cation exchanger resin, and the aim is, you can write here, determination of ion exchange capacity of a cation exchange resin, that is zeocarb 225. That is the commercial name of zeocarb. Okay. So the apparatus required are burette, pipette, conical flask, beaker, glass bowl, funnel. Now, an ion exchange resin. Um, Firstly, what is a ion exchange process? Now, ion exchange process is a reversible exchange of ions which take place between a stationary solid phase and a liquid moving phase. The liquid moving phase will move around it. Now, the resin is generally made up of a polymeric matrix, just like your polyethylene, polystyrene, PVC. Now, certain functional groups are added to this polymeric matrix so that now here you can see these purple ones are the fixed charge group. Now, the fixed charge group is negative. Now, this green line is a polymer chain, and that can be a cross-link one. You can see here this polymer, the fixed charge group or are negatively charged, because they are linked to this or having bond with it. This is termed as fixed charge group, and there will be a mobile counter ion associated with this charged group. So if the charge on the fixed group is negative, the counter ion is positive, and if the counter ion is positive, it is the cation exchanger resin, because this is the ion that can be exchanged. So when a positive cation or a positive ion is coming here in the water, you will see that this particular ion can move out. So that is a resin. So a resin consists of a polymeric matrix which is permeable to water and has a fixed charge group, and mobile counter ions are associated with it. Okay. So such type of resin, if you take it in a petri dish, it will appear like this. And like more closer view is this, these globules. Now it is seen that when you place it in a solution, they tend to like swell a little, like depending on the polymeric matrix and the functional groups. It will it shows, like when you put it in solution or water, it will show increase in volume, slight increase in volume. Exchange resin, it is classified as mm, an exchange resin is classified as a cation exchanger resin and an anion exchanger resin. So a cation exchanger resin, for example, sulfonated polystyrene in hydrogen form. So this sulfonic acid group may be added during the polymerization of styrene. So what is styrene? This is C double bond C here, and this is C6H5 ring. Now, when this one of the like the pi bond breaks, it forms polystyrene.
Ma'am,
Now, during yes,
ma'am, above part is getting cut, ma'am. That part is above one slide part is not
above the
visible
slide,
due to sharing, ma'am.
you can't see
No, ma'am, no. They getting blur.
the cation exchange resin. Maybe now is it okay?
Yes, ma'am. Yes, now it's
Yes.
visible.
Okay. Now, like what I am telling you here is you are having a cation exchanger resin and an anion exchanger resin. Now, what is the difference between these two? Difference is the fixed charge group. Now, here the fixed charge group is sulfonyl acid group. Now, this SO3 minus is fixed. This will never move. Now, this is the only counter ion which can move and can be exchanged. So, H plus if it is released, Na can be retained, or calcium, magnesium, all cations can be retained and H plus will move out. Now, another type of resin which has like CH2, a tertiary amine, so that having a positive charge and OH having negative charge. Now, in this becomes the um, counter anion that can be exchanged. So the fixed charge group is positively charged in a anion exchange resin. Are you getting? Now, here in this particular experiment, we are trying to study the cation exchange capacity. Okay, ion exchange capacity. So, the ion exchange capacity will depend on how many number of these yellow counter ions are present. Now, in turn, this yellow counter ions depend on how many fixed charge groups are there. So, in short, your ion exchange capacity will depend on the fixed charge groups, the number of fixed charge group present in the polymeric matrix. Now, you consider you have like you prepare in two round bottom flask this sulfonated polystyrene by putting the sulfonic acid and sulfuric acid and the precursor that is styrene. Okay, and you put for the polymerization of styrene, you put some benzoyl peroxide or what all initiator for the chain reaction is required and all. Okay, so when the polymerization takes place, um, if you add less quantity of sulfuric acid, then you will find that the sulfuric acid or sulfonyl acid groups are less. SO3 minus forming on this will be less. If you add more quantity, you may get a polymer with more number of fixed charge group. Okay, so it will depend on your polymerization process, or after polymerization, if you treat it uh, with acid that way. So both the ways you can you can incorporate these fixed charge group on it, either during polymerization or after polymerization. You treat these beads with sulfuric acid, so that is incorporated into in between. Okay, with proper initiator and all. So, what I was telling you, the cation exchange resin, the capacity of this will depend on how many fixed charge groups are present per gram. Okay, why per gram? Because that is the unit which you can weigh. Because one particle may be larger, one particle may be smaller, and so on. And they are like it is fine particles, so we measure the ion exchange capacity per gram, and it is how many number of fixed charge groups are there. That many number of counter ions will be there, and that will decide what is the capacity, exchange capacity of that particular resin. Okay, so this experiment aims at finding out the again it came down here. This you can see this part.
No, ma'am.
No, ma'am, no.
Oh, ma'am.
No, ma'am.
Now.
Yes, ma'am. Now
Yes,
it is.
ma'am.
Yes, ma'am.
Okay, so the exchange capacity, you can write this polymeric matrix as resin A minus, that is SO3 minus, and B is your counter ion, that is here it is sodium, and like water, if it flows through the ion exchange bed, then it is say C plus is like your ion present, cation present in water, and when it flows through the resin, the exchange takes place between B and C. Like B is released and C is retained. So resin which is in sulfonic like in having SO3 minus will retain the sodium or calcium or magnesium, whatever cation is there, and the earlier present material will be released. Okay, so that is how an exchange takes place. Now coming to the principle, first the resin present in, now for especially for zeocarb 225, when it is stored in dry condition, it is stored in or it is present in sodium form. So you have to put the resin into HCl so that it is converted to hydrogen form. And then when you treat it with the sodium sulfate solution, you get release of H2SO4. Then finding out how much H2SO4 has been formed is very easy. That is by performing a neutralization titration with phenolphthalein indicator. You can find out this sulfuric acid. So your principle is first the resin in sodium form is converted to hydrogen form by putting it in two normal hydrochloric acid, and then you have to first remove this acid and then put the resin which is in hydrogen form into a column. Now in the column, when you pass a quantity of sodium sulfate, this H plus is exchanged to Na plus, and Na plus is retained and H2SO4 is released. The total ion exchange capacity of a resin is dependent upon the total number of ion active groups present per weight of material, and the greater the number of ions, the greater will be the capacity. Just now I told you. The exchange capacity of a cation exchange resin can be measured by determining the number of milliequivalents of sodium ions exchanged by 1 gram of resin in the hydrogen form. So this is equal to number of milliequivalents of hydrogen ion produced, and thus and that can be estimated by titration with NaOH. So you titrate with NaOH using phenolphthalein indicator. Both are strong, so you can use phenolphthalein indicator and get the reading. Now coming to the structure of cation exchange resin, a hypothetical structure of cation exchange resin is shown here, where you find this is SO3 minus H plus, and there will be cross linking like this. And an anion exchanger resin will have CH2N methyl group thrice, overall a positive charge on nitrogen, and Cl minus. Okay. Now there are different types of ion exchange resins. They are classified based on the strength of your fixed charge group. So you have a uh, sulfonic acid, a strong cation exchanger resin, or this is a strong cation exchanger resin. This is RCOOH. This is carboxylic acid, that is a weak acid cation exchanger resin. Then you have a weak base anion exchanger resin, and quaternary ammonium strong base anion exchanger resin. So these are some type of ion exchange resins. Okay. Now the ion exchange resins are mostly used in large scale in number of industries where demineralized deionized water is required. So the commercial name of those resins are like if it is a uh, aminodiacetic group, then it is an amberlite IRC7. These are the commercial name of these duolite and ambersep and dovex, and these are levatite and diion. Okay, so these are different groups present, and they'll be used. And this resin part, polystyrene or polyethylene or polyvinyl PVC and other compounds like other organic polymers can be there. So R is the polymeric matrix. Now coming to the procedure. Now what is the procedure? Before I discuss this slide, I think If there is any slide, I should go for. Wait a minute. I'll stop sharing. I'll see. I had nice photographs of these. Okay, I'll just see where are those photographs. You see, like I had beautiful um, what you say photographs of the experiment. The experiment was not recorded, but the photographs I am unable to find now. So we will go with the procedure. You have to weigh 0.25 gram of cation exchange resin in a small beaker. Soak the resin in 10 to 15 ml of hydrochloric acid, and the PC is working very slow. Okay, 2 molar hydrochloric acid for about 30 minutes, and during this time, your resin will be converted into hydrogen form. The excess hydrochloric acid should be washed out, and so you decant the acid from the beaker. Let the resin collect into or transfer the resin into a column column is a burette with a glass full stuffed at the bottom, and allow 150 ml of 0.25 molar sodium sulfate solution to pass through the resin bed uh, at a controlled rate of 3 ml per minute and collect the effluent into 50 ml conical flask. So there is only one step, that is you have to pass once your resin is converted into hydrogen form and the column is made, then you have to pass 150 ml of sodium sulfate solution, which is 0.25 molar, at a rate of 3 ml per minute. So this flow rate will ensure complete exchange of H plus with this sodium, and all 150 ml should be collected in a single conical flask, and when all 150 ml has eluted out, then you have to titrate this particular 150 ml which is eluting out from the column with sodium hydroxide solution, which contains uh, like uh, with using phenolphthalein as indicator. Okay, then your volume of effluent, total volume will be 150 ml, and you have to titrate it all together with NaOH solution using phenolphthalein indicator. So the titter value may be somewhere 13.2 is the reading provided to you. So if this is 13.2 ml of NaOH is required, then we see the calculation part. Capacity of resin in milliequivalents per gram is given by the ion exchange capacity of resin. Wait a minute, I'll make corrections here. A lot many things are like I don't know how it can be missed. The ion exchange capacity of resin in milliequivalents per gram is given by the formula AV by W, where A is the normality of NaOH solution, V is the volume of NaOH solution in ml, and W is the weight of resin taken. So normality into volume of NaOH divided by the weight of resin taken, and you get the milliequivalents. So you substitute those things into this. What you get is the ion exchange capacity. So the capacity of cation exchange resin was found to be 5.28 milliequivalents per gram. Like that is the titer value is 13.2 ml. So this experiment comprises of single titration. That is this value you got, and 13.2 into the normality of NaOH divided by the weight of resin taken. The weight of resin taken was 0.25 gram. It is mentioned here 0.25 gram of resin was taken initially. That was in sodium form. So putting in hydrochloric acid, you converted into hydrogen form, and then it was put into the column, transfer the resin completely into the column, give washings, make the column acid free, and then you, when the column is acid free, then you pass 150 ml of 0.25 molar sodium sulfate solution, so that when you collect it, it will be containing acid. Okay, so there are some precautions. Exact weight of resin to be taken should be noted, and then resin particles should be completely acid free before taking into column. Water level um, or liquid level in the burette should be maintained above the resin, at least 1 centimeter above, means the resin should not dry. then pass sodium sulfate solution at the rate of 3 ml per minute. Even if the flow rate is more or less, you should collect it all in a single conical flask. Don't discard this solution. That is one important precaution. Flow rate may you can adjust using a stopwatch, and the pinch cork or the burette jet. Then one important precaution is you have to decant the HCl first when you are converting in the first step resin from sodium form to hydrogen form. There you should remove the HCl by decanting and then transfer the resin into the column. Okay. Pass little distilled water after passage of sodium sulfate solution. That will ensure removal of everything. So this is all regarding the experiment. Did you get the experiment? Z1 batch students. Roll number 1, roll number 2, roll number 3, Z1 batch students. Roll number 4.
Sir, ma'am, roll number 3 present.
Okay. Roll number 4, 5,
Yes, ma'am. Present.
6,
Present, ma'am.
7, 8,
Yes, ma'am.
9,
Yes, ma'am.
10,
Present, ma'am.
11, 12.
Present, ma'am.
So 7 and 11 are absent. Okay. Then 13,
Present, ma'am.
14, 15,
Present, ma'am.
16,
Yes, ma'am, present.
17,
Present, ma'am.
18,
Present, ma'am.
19,
Present, ma'am.
20,
Present, ma'am.
21,
Present, ma'am.
Present,
22, 23,
ma'am.
24.
Present, ma'am.
Okay, so Z1 batch student, today we have discussed determination of ion exchange capacity of a cation exchanger resin, that is Zeocarb 225. Zeocarb 225 is the commercial name of this resin, and this is the ion exchange like resin that you can see on the on the screen. So ion exchange resin experiment we have discussed now. Okay, if I find the photographs of the experiment, I'll show you that how the column is made and how it works. Okay, rest. Do you have any doubt, Z1 batch students?
No, ma'am.
Okay. Now the see, I had good photographs, but I don't know where they are now. Unable to find. It was put into this experiment only. Okay. So we will go to the next experiment, and then we will see uh, the next experiment.
Ma'am,
Okay.
will you share this
So
PDF?
yes.
Will you share this PDF?
Yeah, I'll try to put the photographs and then make a PDF, and that I will put in your group. But for the time being, I have to see why it is not showing these particular uh, images. can you see? Yeah, your mic is on. Okay. Okay, dear students, can you see the slide here?
Yes, ma'am.
Yes, ma'am.
Yes,
Yes.
ma'am.
Ma'am.
Yes, ma'am.
Yeah.
Yes, ma'am.
So this is your Petri dish containing 0.25 gram of resin. This resin is poured initially after weighing. So this you get it into a packet and then you open it. It is put into 10-20 ml of HCl solution, which is 2 molar, and allowed to soak into this HCl for almost half an hour. After half an hour, this resin, the HCl part, the resin settles down, and the acid is decanted, means the upper acid solution is discarded into the sink, and the resin is then transferred into, now this is a burette of 50 ml capacity, you can see 50 written here, and this is the glass wool which is stuffed into it, and the lower part will be the jet of the burette. So in this burette, glass wool is packed here, and over this you transfer your resin, so the resin appears like this. So there is a small quantity taken because unnecessarily, like the quantity is so optimized that you get proper results with even 0.25 gram of resin. Now once the bed is ready, you add distilled water to it and wash it, and ensure that every time the distilled water or the level should be above this particular thing, above the level. X4 batch students can leave the class. This is the practical class. Okay, so you have water should be maintained every time, means the resin should not dry out, and that is how it is collected. Okay, so this is how like your column will look like. This column is nothing but a 50 ml burette in which glass wool is put and then the resin is transferred, and then 150 ml. So first you have to keep a funnel over the burette and transfer the solution, let it flow dropwise, and check the flow rate. So the lower knob opening of the jet of the burette is so adjusted that drop by drop it falls, and it is collected over a time of 50 minutes. That is 150 ml requires around 50 minutes for flow at the rate of 3 ml per minute, right? So 3 ml per minute it will flow, and you collect it into the conical flask, and there is only single titration to be done. That is, all 150 ml is titrated with NaOH solution with using phenolphthalein indicator, and you get a color change from, so initially it is colorless, you are titrating with NaOH, so it will become colorless to pink. So colorless to pink will give you the endpoint, and you have to then go for the calculation. So the calculation is volume of NaOH into the normality of NaOH divided by the weight of resin taken. You get the ion exchange capacity. Okay. So the capacity is reported in milli equivalents per gram because your volume of NaOH is in ml. That is why it is mentioned as milli equivalents per gram. Things are clear? And these are the precautions to be taken in the experiment. So I'll now stop sharing this, and then we will go to verify Cronlich adsorption isotherm. Okay. Now coming to the Froelich adsorption isotherm. This is the fourth experiment or fifth experiment.
Fifth experiment.
Sixth,
This is the sixth experiment.
sixth experiment, ma'am.
Because first four were alkalinity, hardness, dissolved oxygen, free chlorine. The fifth was ion exchange capacity. Then sixth one is to study the adsorption of acetic acid on activated charcoal and verification of Froelich adsorption isotherm. So for this experiment, you would require a stoppered bottle, 6 numbers, burette with stands, 2 sets, pipette, measuring cylinder, funnel, filter paper. Okay. So the reagents required are acetic acid, sodium hydroxide. I'll check whether the photographs are here or yeah, the images are here. That is better. So okay. So acetic acid, sodium hydroxide, powdered activated charcoal. Now, what is activated charcoal? The charcoal is pulverized and it is kept in a hot air oven for the removal of occluded gases and moisture from the charcoal. So that is on heating for 1 hour at 105 degrees centigrade, you get your activated charcoal. You need an indicator, that is phenolphthalein. Now, the theory of adsorption is X is the weight of adsorbate, M is the weight of adsorbent. So, what is the quantity of adsorbate adsorbed on unit weight of adsorbent is given by K into C raised to 1 by 2. Here C because it's a liquid solid interface. The liquid is acetic acid and the adsorbent is charcoal, which is a solid. So concentration term is there. When it is the solid gas interface, then the pressure term will come instead of concentration. So X by M is equal to Kc raised to 1 by N. Here X is the mass of solute adsorbed by m gram of the solid at various concentrations. K and N are constant at a given temperature for a given solid adsorbent and solution. K is adsorption capacity, so you call K is the adsorption capacity, and the value of adsorption capacity is obtained from the, if you extrapolate the line to the y-axis, the intercept on y-axis will give you the K value, log K value, and N is obtained, that is the adsorption intensity from the slope values. So 1 by N is actually the slope, so the reciprocal of that will give you the N value. So equation 1 can be written as in the linearized form. The linear form of this expression is log x by m is equal to log k plus 1 by n log c, where log x by m is on your y-axis or ordinate, and log c, that is the equilibrium concentration, is on abscissa or x-axis, and the curve obtained has a positive slope, and the intercept on y-axis is will give you log k value. So from the intercept on y-axis, from the graph you have to calculate what is the k value, and from the slope of the graph you get the 1 by n value. The slope is equal to 1 by n. So from that slope value, you then calculate what is the n equal to. Okay, so that is what you have to do after performing the experiment. Now for performing the experiment, you prepare 1 molar acetic acid, make it half dilute, that is 0.5 molar, then half of that 0.25, 0.125, 0.02, 0.062 and 0.031 molar. So everything is half diluted and these solutions are made. So an approximate concentration is something like this. Approximate concentration, volume of acetic acid, ml, volume of water, Here dilution is given. Okay, this is the dilution. If you take 100 ml of 1 molar acetic acid and add 100 ml of water, you get a solution which is 0.5 molar in concentration. Then if you take 100 ml of this, because this total quantity will be 101 ml, right? Or 200 ml. So from that 200 ml, you take 100 ml of 0.5 molar and add 100 ml water. You get 0.25 molar solution. From this to 0.25 molar solution, which is total quantity is 200 ml, you take 100 ml and to that again you add 100 ml of water. So you get 1, 2, 3, 5, 4, 5, 6, 6 such bottles containing different concentration of acetic acid, and then you go for the determination. So for determination, what is done? 1, 2, 3, 4, 5. Five conical flasks are there. You have five concentrations of acetic acid. 1, 2, 3, 4, 5. Now each conical flask is first you weigh 1 gram of charcoal and transfer 1 gram of charcoal to each conical flask, which is labeled as 1, 2, 3, 4, 5. Okay. Now you are provided with these concentration of acid solutions. Which concentration? 0.5 molar is there, 0.25 molar, 0.125, 0.062, 0.3125 molar, and 0.0156 molar. So when you are having these concentration solutions, the attendant will give you in these beakers. Okay, 1, 2, 3, 4, 5. Now these five solutions here, the lowest concentration is 0.0325. Okay, so that is used. This is 0.0625. This is 0.125 molar. This will be 0.25. You can see it here, and this is 0.5 molar. Okay, this is 5 written here. Okay, so in each of the conical flask, you are supposed to add 1 gram charcoal in this and then transfer 50 ml of this solution, one solution into the first conical flask, 50 ml of second solution into the second conical flask, 50 ml of the third solution into the third conical flask, 50 ml of fourth into the fourth, and so on. Okay, now each conical flask is having 1 gram charcoal, but the acetic acid in which it is kept is having different concentration. So different concentration, and then you have to shake these conical flasks, keep on swirling this for 1 hour. Okay, so when you shake this for 1 hour, you will find that adsorption of acetic acid which is present in this will take place on the surface of this activated charcoal. Okay, so you have to keep swirling. Now by the time like this is performed in a group of two students will perform this experiment, because you have to shake a 5 conical flasks for 1 hour. At the same time you have to perform other part also. Now these are the original solutions. These original solution of acetic acid has to be titrated with NaOH solution. Okay, so that is what is mentioned here. Now this is approximate concentration. Okay, so you have to take 10 ml of this solution as I have shown you, and add the indicator and titrate with NaOH solution. So whatever is the volume for 10 ml, that you have to write here the volume. Okay, readings are not provided. I'll look for the readings first. I'll stop sharing. You have to wait here only. You will not move out. Hmm. Yeah. You see the experiment readings we will have to put. So the volume of NaOH for 10 ml of acetic acid is measured. Answer your roll call. Roll number 1. Roll number X1. Today we will stop here. Roll number X1, 2, 3.
Yes, ma'am.
1 is present. 2.
Present, ma'am. Present, ma'am.
Yeah, 2 is present. 3,
Present, ma'am.
4,
Present, ma'am.
5.
Present, ma'am.
Ma'am, roll number 1, ma'am. Hello.
Yeah, okay. See, the experiment had readings and everything was there, but now I am unable to find. Somewhere pictures are not there, somewhere readings are not there. I don't know what went wrong with this because the PCs are connected in LAN. Okay, so something is wrong. I'll find it out and I'll take the class again after finding out what went wrong. Otherwise, last year, right from readings and everything was given to the students in a proper way. Today, something either is wrong with the connection, net connection here, or internet in VNIT. I'm taking classes from VNIT, or something something is wrong with this. So today, I won't be taking class now. Okay, so we will stop here and we will see how to go for this. Without completing your experiments, we won't be going now for the theory class. Okay.
Means Monday, ma'am, we will have practical.
Monday is MSc practical, not BTech practical. So Monday and Tuesday I have MSc practicals. So then will be Tuesday, Wednesday, and then Wednesday, Thursday, Friday we have BTech practicals. So I'll combine all the batches together and I'll take it that way. Okay, and I have to first sort out what went wrong and why the things were saved which are not seen here. Hmm? What has corrupted number of things. Okay.
Okay, ma'am. Got it.
Today I'm closing here because this is something. Okay.
Excuse me, ma'am.
Yes.
Ma'am, this is BT20. I haven't. You said I will receive mail, but I haven't received any to join class.
Okay. So from whom you got this?
I got from X1 student.
Yeah, you be in touch with him and get the links from him. I'll
Okay, ma'am.
try to put your email. Did you mention your name into that when you had sent
Yes, ma'am.
me
I have. Yes, I
WhatsApp?
have sent you everything, but I thought disturbing you frequently would not be good. So
No,
I
like
haven't.
initially because it came later, no, and this is practical is a very rare case.
Yes, ma'am.
Okay, so that is why.
Okay, okay, ma'am. Will you then when you will add me, ma'am?
Hmm?
When you will add me in the list?
Yeah,
So
yeah.
where,
I will see, because you see practicals we are not taking as per the timetable, because I have the second semester MSc course also, theory and practical. And since 2 semesters are going simultaneously, lot of adjustments I have to make. I thought today I'll complete 3 experiments and students also will be completing 3 experiments. But the experiments are so I don't know. This is a ridiculous thing. Like what all has been saved in the computer should be there in the computer, right? But the things are not that way. Because all the computers are connected in LAN, and you don't know the network center how it operates the system. Okay. We will see all those things later on.
sure, ma'am.
Okay. So what
Okay.
you have? You made me an WhatsApp message,
Yes, ma'am.
So what is your email ID? You just let me know now. I'll add it somewhere.
Okay, ma'am. Should I text you? L-
Yeah, you can text me later on.
Okay,
Okay.
ma'am. Thank you, ma'am.
Okay. I'll find out the time, common time, check out regarding for other students. Check out the experiments are properly done on what the problem is, and then I'll let you know when I am taking the experiments instructions. Okay. So today we stop here.
Okay, ma'am. Thank you, ma'am.
Thank you,
Bye,
ma'am.
ma'am. Thank you,
Thank you, ma'am.
ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am. Thank you,
Thank you,
ma'am.
ma'am.
Thank you, ma'am.